Hello friends, today I am going to discuss the controller tuning technique. This is one of the topic in bioprocess control and instrumentation. So far we discussed there are different types of feedback controllers can be used for controlling the variables. So like a proportional controller, proportional integral controller, proportional integral derivative controllers. So in these controllers, you have seen there are controller parameters like Kc, tau I and tau D. So in order to get the best controller parameter values for minimizing the errors. So which value can be chosen as the best controller parameter values? So in order to get that, so we can use these criterias, controller tuning techniques like we can choose simple performance criteria, time integral performance criteria, and the last one is semi-empirical controller tuning technique. Today I'm going to discuss the last one, semi-empirical controller tuning technique. So one of the semi-empirical controller tuning technique is Cohen and Coon Controller tuning technique, which is also known as process reaction curve method. So in this technique, so it is a semi-empirical method. So they have used the theoretical background as well as they have adopted some experimental results also. So that's why it is known as semi-empirical technique. So in this technique, what they did is initially they considered the entire block diagram representation of a process. So here, and what they did is they disconnected the loop from the controller and introduced a unit step change of magnitude A into the final control element. So we know the step input is representing it with the letter U of t and its magnitude is A. So if you take the Laplace transform, it will be A by S. So that we are giving into the final control element. Suppose if the final control element is a valve, so the stem position can be adjusted and suddenly changing the stem position and keeping that position for a long time. So that is a type of a step input. So after giving a step input into the final control element, they observe the measured variable ym. So, and they wrote the open loop transfer function, and we know that the open loop transfer function is the product of all the transfer function in the loop between C and Ym. So here it will be GF into GP into GM. So that is here, and so from this product we can, that open loop transfer function, we can represent it with the process reaction curve overall transfer function. So process reaction curve overall transfer function is y bar m of s divided by c bar of s is equal to gf gp into gm. From this it is clear that the overall transfer function of a process reaction curve, it not only depends on the process, it also depends on the measuring element and the final control element also. Then after that, what they did is they plotted a graph, the measured variable versus time. So when they plotted the graph, it was they have seen that it is a sigmoidal shape curve. So normally this sigmoidal shape curve is observed for a first order system with the dead time. So so from this they concluded that so the overall transfer function for a process reaction curve, this can be approximated with a first order system with the dead time. So we know the transfer function of a first order system, that is k by tau s plus 1, and the transfer function of a dead time is e raised to minus tds. So they approximated the overall transfer function of a process reaction curve with this. And so here there are three parameters involved. One is K and the other one is TD and the last one is tau. So what is K? So K is actually change in output divided by change in input, or we can say that it is a gain output divided by input. So when you look onto this figure, the output is actually this, that is representing it with a B. So at when time tending to infinity, the response reaches to this value. So that is actually B. So what is the input? So when you think about input, so we have given a step input having the magnitude A. So our input is A only. So therefore, from this we can calculate K value. So coming to the tau. Tau is the time constant. Time constant we can calculate by using the equation B by S. So B is already we discussed. So that is the maximum value of the response, and S is the slope of the sigmoidal response at the point of inflection. So from the graph, we will be getting the slope also. So therefore, we can calculate B by S. So the last one is TD. So that is a time delay, or we can say that it is a time elapsed until the system responded. So by using this, we can calculate these three parameters. By using these three parameters, so Cohen and Coon, they calculated the best controller parameters values for proportional controller, proportional integral controller, and proportional integral derivative controller. So by if we know these three values like a K, TD, and a tau value, so we can calculate the best controller parameters for any of the feedback controllers. And they have used the performance criteria as 1/4 decay ratio, minimum offset, minimum integral square error for getting the best controller parameter values. And if it is a regulatory problem, that means if there is any disturbance, obviously the controlled variable will be deviating from the set point. So in such a situations, we can use any type of feedback controllers. So if you choose a particular type of feedback controller, like say proportional controller, and the performance criteria, that is if you wanted to minimum to obtain the minimum offset, you can use this equation for calculating the best controller parameter value for casing. So with this, I conclude. Thank you.